So as part of motion of the center of mass, the system of particles, we had seen that just like we defined position as the weighted mean of the individual positions of the various parts of a system. So like that, displacement also becomes weighted mean or summation of m into s divided by summation m. Velocity of the center of mass similarly becomes weighted mean of the individual velocities of the particles divided by the total mass. Now from this we can see the next thing, that how to define the acceleration of the center of mass if it is accelerated, that is. So same kind of method, apply the definition of acceleration as the instantaneous rate of change. So this, when applied to this, will become this, because the masses are constant, okay, in this type of system. So as expected, this also becomes the same formula. It is the weighted mean of the individual accelerations of the particles. Okay, now the yeah, sorry.
Written.
Yeah. Now the more important definition that we had seen from here earlier was velocity of the center of mass being summation mv divided by, now we can write this as total mass. So you can define the momentum of a system as its total mass into velocity of center of mass, which becomes summation of individual momenta of the particles. Okay, so this is the definition of momentum of a system. And then on differentiating this, we get that the net external force acting on the system is equal to the rate of change of its momentum, which can then be written as total mass into acceleration of center of mass, because total mass is constant. So this comes by differentiating this above term. So in this you see that this is the net force acting on the ith particle, and then summation of for all forces acting on all particles leaves you with the net external force. So net external force equals to rate of change of moment. So this is Newton's second law applied to a system of particles. Or we can invert this law and write what is called the impulse momentum theorem, that the net external force integrated over time is equal to the change in momentum during that time. Or the net external impulse equals to the change in momentum. the system. So from this point, we have the special category of systems where the net external impulse is zero. So the momentum is conserved. So that is the condition for applying the momentum conservation principle. Okay, when can we apply conservation of linear momentum to a system when the net external impulse is zero?
Sir, but there's always some force acting on an object, right?
The question is whether the forces are external to a system or not. See, on an object, when we are talking about this, no?
So there's always gravity.
Yeah, so that's what I'm saying. No? Gravity is an, so if we consider a two-particle system, for example, then gravitational force is an external force. No?
Yes, sir.
But if the net external force is zero, no, it might be balanced by normal reaction. Understand?
Yes, sir.
So it's net external force. It's not that there are no external forces. Okay.
Yes,
Then
sir.
it's linear momentum. Is conserved. Okay. Now, is conserved doesn't necessarily always mean that it will be zero. Okay. It can be a non-zero quantity also. The system can be in motion with respect to the inertial frame, but its momentum will be conserved. Okay. So that's what we'll understand with few examples today. Let's look at very basic situation to understand how this applies. So suppose we have a system that consists of two blocks kept on a smooth surface. And these blocks are, let's say, connected by a spring, an ideal spring. So we have two blocks, masses M1 and M2, connected by an ideal spring on a smooth surface. Now what we are doing is initially, let's say we are applying two external forces, equal and opposite forces, to keep the spring in a compressed state and the blocks at rest. Okay, so this is the situation. Initially, the blocks are acted upon by F equal to, let's say, 10 newtons and are at rest. Okay, so let's say the masses are given to us like this, and the spring constant is given to us as 10 newtons per centimeter. Now suddenly, simultaneously, both these forces are withdrawn. So simultaneously, both these forces are suddenly removed. Okay. So the blocks will start accelerating. Okay. So now at t equal to 0, let's say, both forces are simultaneously removed or withdrawn. Okay. So first of all, find the accelerations of each block just after t equal to 0, just after the forces are withdrawn, and show that the acceleration of the center of mass is 0. And secondly, find velocities of each block when the spring reaches reaches its natural length. Okay. And third, find the maximum displacement of each block. Assuming the spring is attached to them. Now, this is a typical problem where we'll use number of concepts, including the new concepts we have learned in system of particles in the last couple of lectures. But apart from that, of course, we'll use all the concepts we've learned in core physics before this. Dynamics, free body diagram, work energy theorem, all these things will come together in a problem like this. Now see, if we treat the two particles or the two blocks plus the spring as a system, then you can see there are a number of external forces acting on it. There are the two horizontal forces applied, F and F. There are gravitational force or weights of M1 and M2. There are normal reactions. Okay. But at the same time, you can see that at the given moment, even before t equal to 0, what about the net external force? It's 0, right?
Yes, sir.
Forces are balanced for the system as a whole. On each block, there is also net external force 0 before t equal to 0. But even on the system, the net external force is 0. Okay. So the moment we withdraw the two forces, because we are withdrawing them simultaneously, what happens? The net external force remains 0.
Yes, sir.
While on each block, individually, the net force is not 0 anymore. Because we are withdrawing F, so there's nothing to balance the spring force Kx. So the moment you release the system, release the external force F from each of the blocks, each block has some net force acting on it. So each block starts accelerating, its momentum starts changing and all that. But if you look at the overall system, M1 plus M2 as a system, interestingly, there is no net external force. So they have to move in such a way, there's a constraint on them that their linear momentum has to be conserved. And what is the initial momentum? It's 0. So interestingly, the center of mass will not move. It will remain where it was as they move. Velocity of the center of mass will remain 0 because the acceleration is 0. Okay. So hope this problem illustrates that concept I was telling you, that can have a situation where there are number of external forces acting, but the net external force on the system is 0.
Yes, sir.
So such a system's momentum will remain conserved. So if you look at the initial state before t equal to 0, so in terms of forces, there are all these forces acting. T naught and T naught. Okay, so T naught is equal to Kx. But so each block is at rest. F is equal to Kx naught, let's say. It's T naught. So how much is the initial compression of the spring? It is 10 newtons divided by 10 Newton per centimeter. So 1 centimeter is the initial compression of the spring. And because both blocks are at rest, so velocity of center of mass is 0. Acceleration of center of mass is 0. The net external force on the system is also 0. So before we write these terms, we should actually define what is our system. So our system is M1 plus M2 plus the spring as a system. Okay, so for this, all these things are happening. Okay. Now, after we withdraw the external force also, the net external force on the system remains zero, though the individual blocks are now having acceleration. So if we compare this situation now to the situation just after t equal to 0. So subsequently in a problem like this, you need not show the vertical forces and all. Only the horizontal ones are open, are important. Okay. So you can see that just after t equal to 0, what is happening? E1 is equal to T naught by m1. So that is how much? 10 newtons divided by 2 kilograms. So 5 meters per second square. E2 is equal to T naught by m2, which is 10 meters per second square. But you can see the acceleration of the center of mass will be 0. Okay. Either you can show it by the fact that summation ma will become 2 into minus 5 plus 1 into plus 10. So that's 0. Okay. Or you can justify it by the fact that net external force on the system hence acceleration of the center of mass will be 0. So this relation that m1a1 cancels m2a2, they are in opposite directions. This will hold true not just for t equal to 0, but for any other instant also. So for example, after some time, if the system has now evolved to this kind of situation, let's say it's gone from here, this state, gone from this state to a situation where this block has moved a little bit and this block has also moved a little bit. But let's say the spring is still compressed. It's not yet reached the natural length. So this is now L minus X, where X has become less than X naught. Is at some T equal to T. Okay. So what we'll see is that by now, this block would have got, apart from some it would have got some velocities also. Okay. And they would have developed some displacements also. So you'll have this kind of relation here. At some time t equal to t, again m1a1 is equal to m2a2 is equal to kx. Okay. And acceleration of center of mass is 0. So velocity of center of mass is 0. m1v1 is equal to m2v2. m1s1 is equal to m2s2. So this also means that the displacement of center of mass is 0. So these equations basically, they are coming from conservation of linear momentum.
So, but what are we trying to do by finding all this?
We'll solve the second part of the question, and then the third part. All these things we'll find out. Okay. So for example, if we want to find out, okay, we know that x naught was 1 centimeter. Now, if we want to find out that by the time x has become half a centimeter, how much speed the blocks have gained, suppose we want to do that. So in addition to conservation of linear momentum, there's also conservation of mechanical energy. On the system.
Yes, sir.
So when we apply that, in this case, the change in kinetic energy of blocks M1 plus M2 plus the change in elastic potential energy of the spring should be 0. So we have half M1 V1 square plus half M2 V2 square. That is a positive gain in kinetic energy plus half kx square minus half kx naught square. This is the loss in potential energy. This should be 0. Okay. So now you can see that between this equation here, this one, say this is equation 1, and this equation here, this is equation 2. We have two equations with two variables, x, v1 and v2. So we can find the individual velocities as a function of x. You understanding? So that is one of the purposes of this whole thing, okay, that we can find out the individual velocities at any moment, including what I've asked in the second part, that we want to find out the velocities at the instant when what is happening, the spring is back to natural length. So put x equal to 0, right? So you'll get the, now this equation will also show you that the maximum speed of the blocks is when x is 0, which is logically also the case. When x is 0, the spring is going to minimum potential energy, 0 potential energy state. So that's when the system's kinetic energy will be maximum. So the individual speeds of the block should also be maximum.
Yes, sir.
So all these things now we can answer on the basis of these two principles that will apply to this system, that is conservation of linear momentum and conservation of mechanical energy. Okay, so now just try to find out this thing, the the speed when x is equal to 0, the individual speed is v1 and v2, and the maximum displacements.
Sir, I'm not able to do it.
Why? What is the problem now? You have to find V1 and V2 now. But at which instant? When X is 0?
Yes, sir.
So in that second equation, the work energy relation that we've written, put X as 0. So what we're getting, half M1 V1 square plus half M2 V2 square is equal to half Kx naught square. Okay.
Yes, sir.
And then you have the relation from momentum conservation that M1 V1 is equal to M2 V2. So
Yes, sir.
mass ratio is 2:1. So velocity ratios is 1:2. So put V2 as twice of V1 in that equation. Got it, no? Two equations, two variables.
Yes, sir.
Done, no?
Yes, sir.
Now you just solve it numerically, but when you substitute with proper units, you'll have to convert and all that. Okay, so got the answer now? It'll be comparatively small speeds. I mean, they'll probably be in centimeters per second.
Sir, we don't have the natural length.
So that's not needed, na? Beta, X not चाहिए था ना उसमें, natural length will be need. We don't need for even maximum displacement, na? Because where it starts from, they're already at the natural length distance, na? So that is not changing, na? The length of the spring is only changing. You're understanding the point? We
No,
don't
but
need the
the
initial
in
positions.
terms of
We
it,
just
no?
need the displacements. Okay, so let's look at this. So let's come to second part. Have you found the V first, V1 and V2 for the second part?
Sir, in terms of natural length, sir.
Why natural length, beta? Natural length कहाँ पे आ रहा है equation? See, is it coming in second equation? No, na?
Sir, X naught.
X naught is the initial compression, beta. That we found out above.
Achha.
The springs, remember the springs potential energy na, doesn't depend on natural length. Na? It only depends on the state of deformity, whether it is compressed or extended and by how much. You understanding now?
Yes, sir.
Okay, so for the second part of the question, now what we have to do, we have to find V1 and V2 at the instant when our X is equal to 0. That is, the spring is at natural length. So now from equation 2, you can see that we have the kinetic energy of the system will just be equal to the initial potential energy of the spring. All the potential energy is converted to the kinetic energy. Okay, so this will actually be the state when the kinetic energy is maximum. Okay, because all the potential energy is converted into kinetic energy. So this equation, what it will give us here, it will give us m1 v1 square. So m1 was 2. So 2v1 square plus m2 was 1 kg. So v2 square is equal to kx square. Now k is 10 into 10 raised per 2 and x naught was 1 centimeter. So 1 into 10 raised per minus 2 squared. So this is our equation. 2v1 square plus v2 square is becoming how much now? 1000 into 10 raised per minus 4. So 10 raised per minus 1 joules. The total kinetic energy of the system is half of 0.1 joules actually, because here I've cancelled the half on both sides. Okay. And from equation 1, we have the ratio of V1 and V2. So from equation 1, we have so substitute this here. So 2v1 square plus 2v1 whole square is 10 raised per minus 1. That's how much 6v1 square is 0.1. So v1 is equal to square root of 1 by 60 meters per second, and V2 is equal to becomes square root of 1 by 15 because it's 2 times. Okay, so this is clear now?
Yes, sir.
Yes, sir.
Okay, very good. Now work out the third part, the maximum displacement of the individual springs.
So 1 upon 300 meter, 1 upon 150.
Okay. So that's 1/3 of a centimeter. Okay. And 1/6 of a centimeter, is it?
Yes, sir. No.
2/6.
One.
1/3 and 2/3 of centimeter. It
2/3,
should
yes,
be like that. Yeah. I think it would be double of the answers, beta. Because see what is happening now, when they reach maximum displacement, the kinetic energy should again become zero. You understanding?
Yes, sir.
So the kinetic energy is becoming zero. Then what is this thing? Spring state. It should go to extension of 1 centimeter.
Yes, sir. Yes.
So extension of 1 centimeter means total. What has happened to the spring? It has gone from a compression of 1 centimeter to extension of 1 centimeter. So the spring's
Yes, sir.
length has changed by how much? 2 centimeters, no?
Yes, sir.
So the sum of their displacements should be 2 centimeters, and the
Yes, sir.
ratio of their displacement should be 2:1. So this one will have 1/3 of 2 centimeters. That one will have 2/3 of 2 centimeters. The heavier block will have 1/3 of 2 centimeters, so 2 by 3 centimeters, 0.67 centimeters, and the other one will have 4 by 3 or 1.33 centimeters.
Yes, sir. I got it.
Okay. Okay, so everybody just confirm that numerically, work it out. We'll discuss. Okay. So logically, how we know that displacement is maximum at what state? So when the displacement is maximum, the spring should have maximum potential energy again. So it should have maximum extension. So maximum potential energy means minimum kinetic energy. So once again, the kinetic energy should be zero. Or logically, you can understand that the system will be oscillating because there's no loss of energy happening. So alternately, spring and kinetic energy, spring's potential energy and kinetic energy are exchanging. So extreme position will occur when extension is maximum. And again, the potential energy is back to half k x naught square. So instead of a compression of x naught, now we are at an extension of x naught. Okay, so hope this is clear to everyone now. So at the time of maximum displacement, okay, what will be happening is that the spring has maximum extension. So for that third part, we'll use that concept. When S1 and S2 are maximum, once again, potential energy of the spring is maximum and kinetic energy of the blocks is 0. So it has gone to maximum extension state. So from equation 2, you can see that if V1 is equal to V2 equal to 0, that is 0 kinetic energy, then you have half k x naught square minus half k x square is 0. So x is equal to plus minus x naught. So that means we have an extension of x naught only in magnitude, okay, which is 1 centimeter. So now if you compare the initial state, where this distance between the two blocks was L minus x naught, to now our maximum extension state, where the spring is now extended, it is not at natural length. So because it has again stored the same amount of potential energy, the kinetic energy has become 0 momentarily, just for an instant. So this will be the same amount of extension as the initial amount of compression. Dynamically, of course, is different. These two blocks have right now an acceleration even in A2 like this, whereas in this diagram, they have an equal and opposite acceleration like this. Okay. So this is the maximum displacement. This is S1's maximum. This is S2's maximum. But the displacement of center of mass is 0. And S1 plus S2 will become 2x naught. Solving these two equations, you get the value of the maximum displacements. S1 is to S2 is 2 is to 1. And S1 plus S2 is 2 centimeters. Sorry, S1 is to S2 is 1 is to 2. The mass ratios are 2 is to 1. So the displacement ratios will be inverse of that.
Sure.
Yes,
So why have you taken x as plus minus x naught?
because that's the solution that this equation is giving you. No? X square is equal to x naught square का solution क्या होगा? That x is plus minus x naught. So
Yes,
here,
sir.
if x is a compression, that means when we are in an extended state, with sign convention, x should be written with minus sign.
Yes, sir.
Whereas if we are writing x as extension, then initially the state was minus x naught, and at this time the state is plus x naught.
Yes.
So this is the maximum displacements. Blocks, okay. Now let's look at another type of application of conservation of momentum. Now this is going to be a somewhat straightforward type of application, but it will lead to some interesting situations. So let's see. So as you start going through more questions of various exercises and all, you will see the very common type of question also. Like we have something like, let's say, wooden plank, which is lying on a frictionless floor, highly unlikely situation. No, surface is perfectly smooth, but whereas this surface on this is rough. So it's a pretty long plank and a person is standing at one end. So the plank, it has a length of, let's say 15 meters, so almost 45 feet long, very long plank. Okay. And it has a mass, let's say, of 25 kilograms, whereas the person, he has a mass of 75 kilograms. Okay. So initially the person is at that end. The plank is also at rest. Now he walks to the other end. So during this time when he walks to the other end, find the displacements of the plank and the person. And needless to say, these displacements are with respect to ground floor. So it seems like an odd type of question if you're not used to a question like this, but just try to think, dynamically what would be happening when a person is trying to walk on a plank like this, and the plank is on a slippery surface. There's no friction. So what will happen when he tends to step forward?
Plank will go back.
Yes, the plank will tend to recoil backwards, because what happens is when he steps forward, he uses his muscular force to generate a motion where he's trying to make his foot slip backwards. The back foot is trying to make it slip backwards, and that's how he's lunging himself forward. So he is applying a horizontal impulse or push in the backward direction on the plank, and through friction, the plank is able to apply an equal and opposite forward impulse on him, because there's no slipping between his foot and this thing surface, right? So what happens is that the plank receives a backward impulse via static friction, and through his foot he receives a forward impulse. Okay, so that's why his body accelerates forward, but in this case the plank will also accelerate backwards, which is something that you won't see in everyday life because there won't be a smooth surface like this. So most probably when you walk on a plank like this, the plank will tend to remain stationary. Okay, but if you imagine a very greasy smooth surface below, even if it is not perfectly frictionless, you'll understand that there will be some kind of slipping that will occur. So that is what is happening over here. But in this case, since the surface is perfectly smooth, if you take the plank plus person as a system, what quantity we can conserve for that system?
Force, momentum.
Linear momentum, right? We can conserve linear momentum. And before the system started this change, that is the person started walking, what was the state of the system? It was at rest. So the center of mass's velocity was 0.
Yes, sir.
So now even when he starts moving, he will start moving forward, the plank will be slipping backwards in such a way that the center of mass remains stationary. So not only momentum is conserved, actually the system's center of mass remains fixed at one position. Understood, no?
Yes, ma'am. Yes, sir.
Okay, so now work this out. Okay. Now one interesting thing is, remember whenever you have a biological creature, like here we have a person, we cannot apply conservation of energy because there is, overall there is conservation of energy, but then you have to consider his internal potential energy. Like, there is some energy that he converts, from conversion of glucose into energy into finally mechanical energy through his biological system. So we
That's
can't
not
say that. So for example, when a person is climbing up a ladder or when a person is climbing up a rope or something like that, it might seem very odd to you what's happening in terms of energy, but actually it's very simple. When you're climbing up a ladder, you are gaining potential energy because you're converting your internal energy, the energy that you stored in the form of glucose or whatever in your system, sometimes even your fats or whatever. So that is converted into mechanical energy, which in this case, if you're climbing very slowly, is going to be gravitational potential energy. Keep in mind that for example, if you're climbing a ladder, the ladder is not doing any work on you, because the only type of force that the ladder is applying is a combination of normal reaction and static friction, where your foot is in contact with the ladder. So neither of those forces has any displacement at the point of application. So they're not doing work. Here also, when the person, for example, he's at rest initially and he lunges forward, so his kinetic energy is increasing, but the plank is not doing any positive work on him.
Okay, sir.
So that's one kind of trick question you can get conceptually. So you understand that, okay? If a person is not an biological creature is moving on a surface or anything such that there is no slipping involved, so there is no work done by that surface on him or her.
Sir, they'll be
Yes.
traveling the same distance, but I'm not able to understand. What am I supposed to do?
What are you supposed to do? Okay, very good question. We want to do what? We want to find the displacement of the person by the time he's reached the other end. No? So imagine what's happening when the person is walking. He's moving forward. The plank is slipping backwards. So it's a
Yes, sir.
case of relative motion, na beta?
Yes, sir.
So suppose he moves a distance x forward. The plank moves a distance x prime backwards. So with respect to the plank, how much will his displacement be?
2x.
Not 2x, but x plus x prime. No?
Yes, sir.
So let's say this is his state initially. This is what is there at t equal to 0. Now, after some time, let's say he has moved forward. So the plank has slipped backwards by a certain amount.
Yes, sir.
So this is at some general time t. Okay, and eventually he'll reach the other end. So in the ground frame, he has had a forward displacement of S1 and his mass is M1, let's say, whereas the plank has had a backward displacement of S2. Understood now what you have to do?
Sir, that I already got. This x
Ah.
prime also should be equal to x because
Sorry,
s of
what
is 0, no?
what should be?
The displacement of center of mass will be 0.
So displacement of center of mass should be 0. So
So
M1
x
S1 plus M2 S2 vector sum should be 0. Okay, so you got that now. So S1 is to S2 will become M2 is to M1.
Yes, sir.
So in this case, that is what mass of the plank, okay, which is how much was it? 25 kg. Nice to. So 1 is to 3 ratio. S1 is to S2 is 1 is to 3 ratio. Okay. Now the thing is, see, his relative displacement is this.
Yes, sir.
S relative is S1 plus S2. So when he reaches the other end of the plank, what is that relative displacement? It's equal to the length of the plank. No?
Yes, sir.
That's the quantity that was given to you. Okay. So at this point of time, what is happening is that
but the plank
the
is also
sum of
going backwards.
The sum of their displacements should be equal to the length of the plank.
Okay.
So when he reaches the other end, so I have told you it's a very trivial question actually. Very simple question in that sense. The length of the plank is given to you. Okay. So S relative, that should be equal to the length of the plank, which was how much? 15 meters.
Yes, sir.
So S1 plus S2 should be equal to 15 meters. And S1 is 2 S2. So he would have actually, the person would have displaced by only 1/4 of 15 meters. Whereas the plank would have slid back. 3.75 meters. Whereas the plank would have slid back. So 11.2.
Sir, can you please scroll up a bit?
Yes, yes. That's correct. Okay, this part is all right.
Yes, sir.
So what is written in the part where the displacement of the person 15 by u?
Displacement of the person.
Answer the green part.
15 by 4 better. See,
Oh.
1:3 ratio, no? So this one will be 1/4 and that one will be 3/4. Right?
Yes, sir.
So done.
Done now. Okay, very good.
Yes, sir.
Okay, now let's. So all of you are clear with this question, I hope. Okay.
Yes, sir.
Now let's see a slightly more interesting version of this question. Involve So this, like the next question that I'm giving, it becomes like a logic puzzle type of question, along with the concept of center of mass, of course. So we again have that same situation, a plank on a smooth horizontal surface and all that. This is the plank. Or let's say the mass of the plank is this time 20 kilograms. Okay. And we have three people. We have person A of mass 80 kilograms. Person B initially at the midpoint of the plank. And he has a mass of, let's say, 60 kilograms. We have another person C at the other end of the plank. His mass is lightweight, let's say 40 kgs. Okay. So initially, and the length of the plank is given to us. It's 24 meters. So initially, P is at the midpoint of the plank. All are at rest, including the plank. Now, after some time, A moves to the other end of the plank. C moves to the midpoint. And B moves to A's original position. So find the displacement of the plank during this time and their individual displacements. So this is just a slightly lengthier kind of version of the previous question. And you can see that, we have to keep track of a number of things here while you're solving it. But the concept is the same, that the center of mass of this whole system should remain stationary. Just give it a try. We'll discuss a couple of methods of working out a question like this.
Sir, we already know the individual displacements of ABC.
No, we know with respect to the plank, not in the ground frame. No?
Acha, okay, sir.
So that is the whole thing. No? You have to assume the plank is moving in a certain direction. Accordingly, then you can use relative motion and that way.
The planks move 0.
Why will the plank move 0, beta? See, the
No,
thing is, na,
yes,
they
sir.
are of different masses. Na? So, for example, see, if A alone had moved, the plank would have moved backwards by a certain amount.
Yes, sir.
If B alone had moved, the plank would have moved forward by a certain amount. If C alone had moved, the plank also would have moved forward. Okay. So now it's like a superposition of all these things. No? So how can we say that the plank's displacement will be 0?
Yes, sir.
Sir, what was the length of the plank again? Is it 24 meters?
Yes.
Yeah, the length of the plank is 24 meters. Actually, it's not visible on the, just a second. Yeah, 24 meters.
So the plank moves 36.
Plank moves how much? 3.6 meters.
36. 36 meter.
How is that possible, beta? Plank का length ही 24 meters है. Okay, so anybody got it? Okay, so let's work this out now. We spent quite a bit of time on this. Not received any answers from anybody yet, so I'm
Sir, just a sec.
okay. I'll give you another minute. Second is a lot less. Okay, so I'm just okay. Dhruv has sent me some answer. Okay, so I'm just going to start with the method, couple of methods that we can apply. Now, the general complicated method of doing this would be, see, 80 kgs is the heaviest mass out of all the objects in the system. We have 4 objects in the system, 3 people and 1 plank. Okay, and that one is moving towards the right. Okay, and that too by the maximum displacement. So we can safely assume that the plank will move towards the left. So if we make that assumption, the situation would look something like this, that in the ground frame, let's say this was the initial state. The initial state is that the plank's mass, which is whatever, I think it was 20 kg, is here. Okay. E, who had a mass of 80 kgs, is here. B, who had a mass of 60 kgs, is here. And C, who had a mass of 40 kilograms, is here. Right. Now, by the time E walks to the other end, let us assume that the plank shifts towards the left by some amount. So the plank's center has moved here. And now E is here. So 80 kg mass is here, whereas C has moved to the center of the plank. So C is here. So it's 40 kg. Okay. And B has reached the other end. This is 60 kg. So now if I assume that the displacement of the plank during this time, this is, let's say, SP in magnitude like this. Okay. So in comparison, now I can see what is A's displacement. E's displacement will be positive of L minus X. Let's say displacement of the plank is minus X like this. Okay. Now similarly, what will be C's displacement? This is C's displacement. So it will be minus of L by 2 plus X. And similarly, what is B's displacement? In the ground frame, that is, okay. So B's displacement in the ground frame is again minus of L by 2 plus X. But this is all with the assumption that the plank is moving backwards by X. So if SP is equal to minus X, this automatically implies that this one is minus.
Sir, is the answer 18? The plank moves backwards by 18 meter.
Let me check. Okay. So now we'll get the answer from this. Okay. So what should happen here as a system, that is A plus B plus C plus the plank. For this system, the displacement of center of mass should be 0. So mass of A into S of A plus mass of B into S of B plus mass of C into displacement of C plus mass of the plank into displacement of the plank should be 0. So now this one equation, we should be able to solve it quite easily. So this is 80 kg into positive of 24 plus, 24 minus X. Right. More proper way. Then mass of B is how much? 60 into minus of L by 2 plus X plus mass of C is 40 into again minus of L by 2 plus X. And finally, the mass of the plank was 20 kg and its displacement is minus X. Okay, so is this equation correct? The one I've written so far?
Yes, sir.
So let's check it out now. Is equal to 0. So this is 80 into 24 minus X. Okay, then I can write this as 100 into L by 2 plus X. Okay, and minus 20X should be 0. So we should be able to solve this now. So just L by 2 is, replace it with 12. So how much we are having now? 80 into 224 minus 12 into 100. So 12 common. So we have 160 minus 100. And that is equal to, on the other side, we will get 80 plus 100 plus 20 X. So X is becoming 12 into 60 divided by 200. That should be my answer. Okay. So I'm getting 18 by 5.
0.6.
Yeah, 3.6 meters. So I'll also verify this answer by another method. It'd be like a shortcut trick over here, but
Sir, I got the same answer as Janvi's.
which is how much? 18 meters.
Yes, sir.
Yes, sir.
Okay, just check out your method versus this solution. See if
So this only.
so that means there's a numerical difference. Are you getting the same equation as this one?
Yes, sir.
This equation is the same. Okay, I'm just going through the numerical solution once more.
Sir, I am getting 3.6.
This is correct. At least up to this step, it is correct now.
Sir, I took A's displacement as negative and B and C as positive.
Okay.
Then, sir, I'm getting 3 by
So
4.
then the Planck's displacement you are getting as positive or negative? What have you taken it as?
So Planck's displacement, I'm getting it backwards 18 meters. Sir, for the Planck, why have you multiplied 20
Yes.
with minus x? It should be plus x, no?
So I have taken the Planck's displacement in the negative direction. See how I have see my diagram. That's why I have taken A's displacement to be actually 24 minus x in the forward direction. Because A is the heaviest mass, so I'm assuming the Planck ultimately moves opposite to how A moves. You understanding my point?
Then, sir, A's displacement relative to the Planck should be 24 plus x, right?
No, beta. See, E's displacement in the ground frame is positive of L minus x. Okay? And the Planck's displacement in the ground frame is minus x. Okay. So what is A's displacement with respect to the Planck? It is A's displacement in the ground frame minus the Planck's displacement. Then only it will come as plus L. No?
Yes, sir.
Understood? No? Otherwise, it's a mistake. No? So this equation, it's actually coming from this because I know that displacement of A with respect to the Planck is plus L. And I'm assuming that displacement of the Planck is minus x. So from that, I'm seeing that A's displacement in the ground frame is positive of L minus x. Okay, is this clear now?
Yes, sir.
Okay. Now let's look at another way of doing this question. So basically, see what should happen in this diagram itself. Wait, I'll just use the same diagram, but in a different way next. Okay. What should happen to the system center of mass in this diagram? It should remain where it was.
Yes, sir.
So it's like four things in the system have moved from somewhere to somewhere, but the system center of mass is not moved. No?
Yes, sir.
So if we compare this now, just a moment. Move all this. Actually, this we need it. So C's mass is how much? 40 kg. Okay. Now, if you look carefully in this diagram, where is the system center of mass initially? It must be somewhere over here because A is heavier, no?
Yes, sir.
It must be somewhere here, let's say. So this is the position of the center of mass. And later also it should not move. The center of mass should remain here. This is the center of mass's position. Okay. So if you look in the first diagram, if I take my reference as this point I take as the reference, then what is the position of the center of mass? It is in the first diagram, XCM is minus of 80 into 12. Okay. And on that side, I have plus of 40 into 12 divided by the total mass of the system, which is 200 kg. You understanding? With respect to the center of the plank as my origin of my coordinate frame, what is the position of the center of mass? It is XCM, which will be this negative quantity, right?
Yes, sir.
So ये कितना होगा? Let's calculate it. Minus 960 plus 480 divided by 200. Okay. So that's how much? 4.8 divided by 2 now. So minus of 1.2 meters. Okay, that's XCM with respect to that one. Okay. Now come to the below diagram, and again in the below diagram, take this as our origin. So what is the position of the center of mass with respect to this origin now? So let's write that as prime. Okay. So XCM prime this time will be a positive quantity, because from my new origin, which is the new center of the plank, okay, what is happening? My mass A is at positive of 80 into 12, and on the other side I have mass of 60, which is at minus 12, and the other two masses are at the origin, so they don't contribute. So divide by 200. So this is becoming how much now? 12 into 80 minus 60, so that is 240 divided by 200. No? So oh wait, this should be different. This was 480 divided by 2, so this should be 2. So this one should be minus of 2.4. Okay. So now you can see how much the center of mass has moved. The displacement of the plank is how much the center of the plank has moved, not the center of mass, but the center of the plank. The center of the plank has moved from my earlier point O to this new point O prime. Understand? Earlier this point was O. Okay. So it has moved from here to here. So this is the displacement of the plank. No? So it is minus of, so it is moved by minus 3.6 meters. So therefore now I can see that what is the displacement of A? It is the displacement of A with respect to the plank plus the displacement of the plank. So that is plus 24 minus 3.6. What is the displacement of B? It is the displacement of B with respect to the plank plus the displacement of the plank. That is minus 12 minus 3.6. That is the same as the displacement of C. So these are the individual displacements in the ground frame for A, B, and C. So I hope that this question's logic is clear to all of you.
Yes, sir.
Isme what we are doing now, we are referencing the center of mass of the system with respect to the midpoint of the plank in the first diagram and the second diagram. And comparing the two diagrams is the center of mass which is at the same position. So now we know how the center of the plank has moved from some point on the right hand side of the COM to some point on the left hand side of the COM. In the first case, the center of the plank is at 2.4 meters to the right of the system center of mass. And the second diagram, the whole system has shifted in such a way that the plank's midpoint has reached the left of the center of mass by a distance of 1.2 meters. So the plank's midpoint, it has moved from 2.4 meters on one side to 1.2 meters on the other side of the COM. So it has moved by 3.6 meters. And then I'm just using relative motion concept to find out how much A, B, and C have individually moved. So this is like a shortcut way of doing the question, because I have to just find out two things: where the COM is with respect to the Planck's midpoint in the first diagram and in the second diagram.
So done.
Okay. Right. So now we have less time left, but we will discuss actually a different aspect of center of mass, because you can get started with questions involving conservation of linear momentum using these examples, and there are plenty of questions to do of that type. But now, before we come to collisions and more applications, you have to also understand how to calculate the center of mass of a continuous mass distribution using integration. So center of mass of continuous mass distribution using definite integration. So the general idea here is that the summation that we do in the case of discrete particle system to calculate the weighted mean, that summation is converted into an integration. So if we have any general kind of shape, which is a body of mass m, total mass m, and with respect to some kind of a coordinate frame, let's say we are actually talking about a three-dimensional rigid body. So it's a what we call a volume distribution of mass. Mass is distributed over three-dimensional volume. So to imagine this as a three-dimensional object which is solid. So with respect to our origin, if the center of mass is sitting somewhere here, so we want to now find the position of this center of mass. So we want to find RCM, a position vector. So had it been a collection of particles, it would have been the weighted mean of the individual positions. So here it is a collection of particles, but it's a collection of particles which are very small, an infinite number of such particles. So what we do is we take a differential mass element. That means we take a particle of extremely small mass compared to the total mass of the system. The mass of this particle is very small, and let's say its position is R. So for what is called a differential mass element, TM, if the position is R, then the position of the center of mass becomes integration of RDM divided by the total mass. Like this. So that summation is replaced with integration. Okay. So it's like, if I consider a small particle of mass delta m at position Rn, then the position of the center of mass would be summation of delta m into R divided by total mass. So now when we apply a limit, that in this equation, we apply the limit that delta m tends to 0. So in that case, what happens is that delta m is written as dm, and the summation becomes an integration. So this becomes integration of rdm divided by total mass, where total mass would be summation of these delta mi's. Okay. So that here would become integration of dm. So if this is tending to 0, that means n is tending to infinity. So the summation is converted into an integration. Okay, so this is the general principle, and now we'll see step by step how we apply this in different situations. Okay, so people hope this concept is clear. The conversion of summation into integration, when instead of discrete particles, we are taking differential mass elements or very tiny particles which are continuously distributed instead of being distributed discretely or individually at positions Ri.
Yes,
Right,
sir.
so hope this is clear. Okay,
Yes,
see
sir.
that the population has declined somewhat of the class. We are doing something very important anyhow. So let's look at an application of this. So now basically, our continuous mass distribution, this can be of various different types. It can be what is called a linear distribution. It can be what is called a surface, and it can be what is called a volume distribution of mass. So an example of a linear distribution of mass would be like a thin rod or a thin wire bent into any shape. It could be like, I've taken a thin wire and I've bent it into some shape like this. Or it could be a rod of particular length, but negligible thickness in comparison. Now, surface could be, for example, any thin disc or plate. Could be any arbitrary shaped plate, okay. But it's a laminar surface. They're examples of what we call laminar surfaces. Okay. On the other hand, I could also have something like a hemispherical shell. This is a three-dimensional surface. It's not non-laminar. So this is a thin shell, say hemispherical. That's also an example of a non-laminar surface. Laminar is two-dimensional and non-laminar is something which is not lying on a two-dimensional plane. And volume distribution, any rigid body, any three-dimensional solid rigid body. Solid cylinder or whatever. So accordingly, for each type of distribution, whether it's a linear distribution, a surface distribution, or volume distribution, we have to take different types of mass elements. So for linear distribution, the mass element should be a linear element. And lambda is mass per unit length. For surface distribution, a mass element dm should be a surface element. And sigma is mass per unit area. And for a volume distribution comparison, it should be a volume element. And rho is density, that is mass per unit volume. So this is a sort of general guideline that we follow for doing the integration. Okay, so we'll just do one quick example of the application of integration here. Now, for example, we have something little unusual, like we have a thin rod, but it is not isotropic. That means the mass distribution is non-uniform. So we have a thin but non-isotropic, or what is also called anisotropic rod. That means the mass distribution is non-uniform, for which it is given that lambda is a function of x. Where the length of the rod is L and x is the distance of any point inside the rod from one end. Here lambda naught is a constant. L is the length of the rod. X is the distance from end A of the rod. Okay, so this. So you have to locate the position of the center of mass. Okay, so since this is a linear distribution of mass, we will use the formula. I mean, in the formula of center of mass position, integration formula, we will substitute dm as lambda dl. Okay. Or in this case, it will become lambda dx, because we will take the length of the rod, I mean the direction along the length of the rod as x. Making a more detailed diagram. So what we'll do is at some distance x from this end, we will imagine that we have sliced a thin section of the rod whose thickness is dx. So that section, this differential element, it has a length equal to dx and it has a mass. So that lambda is lambda naught 1 plus x by L into dx. So this is the mass of that element. Now I know that the center of mass is likely to be somewhere to the right of the geometrical center. So I want to find the position of the center of mass. So I'll convert that vector relation into a one-dimensional vector equation now. So the general equation that I have, that RCM is integration RDM divided by total mass. In this, I will convert this to XCM is integration XDM divided by total mass, where total mass is what integration dm and dm is what it is lambda dl, which is lambda naught 1 plus x by L into dx. So this integration x dm will become integration of x into lambda naught 1 plus x by L, starting from the point A on one side to the point B on the other side, A to B. This will give me the numerator, and for the denominator I need to calculate the total mass. That will become again from x equal to 0, x equal to y. So separately I will calculate this numerator, integration x dm, and separately I'll calculate the denominator, which is the total mass, and their ratio will give me the position of the center of mass, that is the x coordinate of the center of mass with respect to the end A of the rod. So this is a typical application of the concept of definite integration used to find position of center of mass, where the summation is replaced with an integration, with a definite integration. Now, when we are integrating, we replace that mi, the mass of the ith particle, with dm, the mass of the differential element, and that dm is accordingly a small length element or a surface element or a volume element, depending on how the mass is distributed, whether it's distributed over a volume, over a surface, or over a linear object. Okay, so let's see what the integration first one gives us. Integration x dm. This term becomes lambda naught, okay, into x plus x square by L. So lambda naught into x square by 2 plus x cube by 3 L from 0 to L. Plus 5 by 6 lambda naught L square. That is this term. Whereas the second term, the denominator term, the total mass, see what that is. Okay. So now from this and this, combine them. So how much that's coming out to be now? Five by 9 L. So you can see that is slightly greater than 0.5. So the non-linearity in the mass distribution is shifting the position of the center of mass slightly to the right of the midpoint, but not that much also. It's not like it's at 3/4 or something, because it's a gentle increase in mass distribution as you go from A to B. It's a linear distribution change. Okay, people, so hope you have understood this integration application.
Yes, sir.
Yes, sir.
Oh, okay, very good. So we will see a lot of these type of examples in the next lecture. And also this type of situation is, very systematically explained in Resnick-Halliday also. So you can start going through that section, center of mass calculation using integration, because those methods that we'll be learning for integration will be very useful in future chapters also, like gravitation, rotational mechanics, etc. So these type of integrations are going to be common in physics from this point onwards. So it's a good place to start learning the center of mass chapter. Okay. So anyhow, that's it for today's session, people. Yes.
I'm not able to find the chapter. There's no chapter of center of mass.
No, it is given with some different name. Like there is a concept of system of particles, then collisions, those kind of chapters. After work by energy, look in Resnick-Halliday, you will see.
Okay,
Okay.
sir.
It's a bit distributed, the chapter.
Yes, sir. Okay, sir. Thank you,
Okay,
sir.
I will send you the relevant index names from this. Okay.
Thank you, sir.
Thank you,
Yeah.
sir.
In general, when you are using reference books, now you can also make use of the index page at the end. Like suppose, you're specifically looking for some definition, like, what is, let's say, what is an inelastic collision. So then just look at the index page. It's given alphabetically. So there'll be something listed inelastic collision. So then you can find the page number where it is located.
Okay, sir.
You people are used to search engines and Google. Now you have to sometimes get used to these analog methods also. Okay.
Sir, I use the appendix, sir.
Okay, very good. Good to know. Okay, so that's it for today's session. People work on those two exercises I've sent, also the revision work exercise of circular motion and one introductory basic exercise of center of mass. Those also.
Okay, sir. Bye, sir. Thank you, sir.
Okay, that's it for today, people. All the best.